Hello everyone, welcome back to my channel here on YouTube. And yeah, today it's actually a video I've been planning since a long time, ever since I did a little cool some study into how randomness works in computers and dice distributions and stuff like that. And that's actually what I'm learning in my classes right now. So that's a cool coincidence. So yeah, today we'll be talking about dice distributions, how you can sort of apply the concepts of probability into math using NumPy, Matplotlib, and all of that. So yeah, I also prepared little slides thingy. This is just a site made in Astro and hosted, so it's not anything cool and all. So yeah, with that being said, let's get started. One more thing though, I have shifted to light mode because apparently that increases the legibility of the text, and dark mode was a bit weird to render in HD because my laptop was crying, and I found that even if you render a 720p video in light mode, it it's able to perform much better than this thing. So with that, I've shifted to light mode, and hopefully that doesn't mind you guys. And with that being said, let's get started with a very simple challenge. Choose a number between 1 and 10. Really simple, just choose a number. Well, chances are, at least the statistical chances are, you probably choose the number 7, right? And if not, you're special, you're a wizard, congrats. Well, there's a good chance you did not choose 7, but at least in my thinking, and this has been discussed by numerous channels other on YouTube. I'll actually link a really good video from number 5 on this topic, which actually inspired me to write the code for this in the first place. Right. So, first things first. Why did we choose the number 7? Well, the logical explanation is 1 to 5 is way too small. No one wants to be like too small, not too big. Like 8 to 10 are too big of a numbers. So we are left with 6 and 7. And we are statistically more likely to choose 7 because that's an odd number, and well, 6 is even. So we are like, maybe everyone will choose 6 and I have to choose 7. Right. Simple enough. Well, this cool little trick actually shows us a glimpse into a very important concept in distributions, which we'll be discussing right now. So let's extend this experiment to 2 dice. So basically extending this to 2 dice removes all the personal and opinionated bias from the experiment. So we are no longer asking a person to determine if something is this thing. We are just asking a pseudo random number generator using the XOR shift 128 plus algorithm, which is really interesting topic. I also have a GitHub repo on that, which I'll be linking down below. But basically, if we plot the results of rolling 2 dice, this is the probability distribution that we get. So this is the probability. So this is P of X and X, and plotting that, we get that the die is more likely to arise at 7 to fall on the sum 7, which sort of makes sense because if you see the sum of the dice and the favorable number of outcomes, for the sum being 2 there's just one ordered pair, whereas for the sum being 12 there's just one ordered pair, and it goes in like this rhombical fashion that I really like to showcase. And as you can see, for the sum to be 7, there are 6 favorable outcomes, and there are like 6 ordered pairs that are able to perform that. So by ordered pair I mean die 1 has 1 and die 2 has 1, right? So which plotting this rhombical shape on the distribution curve, you get something like this, which really makes sense if you think about it. Pretty simple, right? So now let's look at central limit theorem, and Disclaimer, I'm by no means a mathematician. This is just something I found really interesting and it's being discussed in my class, so I thought I'll make a video on it. But in my own language at least, central limit theorem states that the distribution of a random variable x will be a normal distribution given a large number of trials. So hence the sample of x will be distributed normally, but it should be from a large number of trials. And what we want to do today in this really short video is we want to find the minimum number of tries required to get a normal distribution by rolling n number of dice programmatically. I'm sorry for the typo there. That should be n number of dice programmatically using the Zorshift 128 plus pseudo random generator. So with that being said, let's get started. Well, first, to follow along, you are going to need, well, four things. First, you will be needing Python, which you can download from python.org. You will be needing Jupyter, which I can just open it up from here, I guess. I can just Google it. And yeah, you can download Jupyter from here. I'll be using Jupyter Lab, which is excellent. I really like it. And we'll be using 3 Python libraries. First up, NumPy, which I'm sure all of you are aware of, most of you at least, and it's just awesome. I don't really need to explain this. Next, we'll be using matplotlib, which, if you're not familiar with, is a visualization tool for Python, which allows you to draw contours, graphs, and stuff like that. Right. Now, we'll also be using Seaborn, which is a data visualization library based on matplotlib, and we'll be using this mainly for the graph styles and stuff, right? So with that being said, let's get started. And you need to open up your IPYNB notebook in the Jupyter Lab, and now you can follow along, right? So first things first, we'll be importing NumPy as NP, matplotlib.yplot as PLT, Seaborn as SNS, and not to forget, we'll be using the inbuilt random library in Python, which provides a really good algorithm, so we don't need to use it. First things first, we need to simulate the rolling of dice, right? So we'll just need to roll one dice, and that we'll do by doing a function, defining a function called roll dice that doesn't take in anything, nor, and then it returns a random integer between between 1 and 6, right? So if I go roll dice and nothing there, we get 6. Do that once more, we get 3, right? So it's pseudo random. It's awesome. We can just we can just assimilate the rolling of dice like that, right? Next, we need to just roll one dice. How about that, right? Just the uniform distribution of one die, and the experiment will be run about how many ever times you want. So let's say like n is 10,000. We'll fix that, and this is mainly to get an average of the values. So now we are trying to remove the bias as much as possible. So now this is just the number of iterations, right? So this is just for removing bias and stuff, right? So let's look at how we can run just one die. So running just one dice for now, we can say rolls is roll dice, right, for nothing in range of n. And now if I print rolls, there you go, you see all this random numbers. So, oops, accidentally removed the square bracket there. There we go. So now we have our rolls for one die, and now all we have to do is get the sum of the outcomes, right? And for rolling one die, we know the outcome has to be from 1 to 6, right? So we can define a feature set of called sum outcomes, which is just an vector a range, I guess, yeah, and that takes in n 1 to n plus 1, I guess, so that should be 7. And let me just out, there we go, we get an array of 1 to 6, which is our feature set or the outcome set, I guess. I'm not really sure what to call it. Anyways, now in our sum of outcomes, we want to see how many of our roles has the sum outcome in, and put that in another variable called sum counts, right? Sum counts is then roles dot count, which and numpy takes a count this thing. So if I say roles dot count what 1 or 2, I get the amount of times 2 was there in roles, right? So it's just a way to find the sum of all the values, I guess, or the number of occurrences at least, right? So we want to put that in a sum counts variable, right, which is roles dot count sum val for sum val in sum outcomes, right? So for each outcome in sum outcomes, I want you to count the number of times it was repeated in roles. And if we print that out, this is our distribution, and you can already see it taking shape little by little, right? So hence now now we have to calculate the probability. Remember, these are all out of 1000. So first of all, let's check if what we took was indeed a random variable. Now, if it was a random variable, if I say np.sum, I hope I am right. I'm not really. Yeah, there we go. np.sum, now sum counts, you get 1000, which is the sample space. Actually, let me make that clear here. So that's the sample space, right? So I don't want to make it unclear. The number of iterations or the sample space is 1000, and all of our sum counts together result in the 1000, which is equal to n. That is true. Hence, it's a random variable. Good. Now, probability, if you are not familiar, is basically defined as probability p of x is the favorable outcomes of x by the sample space, right? This is how I like to represent it. F stands for favor. I know it's not the correct representation, I just like it like that. So p of x is favorable outcomes of x divided by the sample space, right? So to calculate the probability, what we can do is probabilities is, well, np.array of sum counts by n. And now if I just print out probabilities, there we go, we have our probability distribution right there. Pretty cool, right? And let's check again if the sum of probabilities is equal to 1. And yes, that is equal to 1. Hence, what we are dealing with is indeed a random distribution, a random probability distribution, right? So now let us plot this. A very simple plot would just go along the terms of like this. So we want our x to be the sum outcomes, and the probabilities oops, I'm sorry, the probabilities to be the y, and that's it. There we go, the most weirdest of digits. And actually that should not be the case. I don't know why that occurred for some reason. Yep, actually that should not be the case. They most likely should be in the same graph. Or you know what, maybe I have increased the sizing a bit too much. So what I will do is set the y lim to 0 to 1, and that should give me a really good curve. Now remember, in an ideal case this should be a straight line with all of them pointing to 0.2, or not 0.2 per se, they should be pointing to 1 by 6, 1 by 6, which I don't know what 1 by 6 is, and 1 by 6, which is 0.161616. In an ideal world, in an ideal case, all of the numbers that we get should sort of be a straight line of 0.16, but since this is a pseudo random generator, this is as far as we can get, right? So now that we have plotted it for one case or one die, doing this for n number of dice would be a headache. So how about we use a plot roles function? Let's define the plot roles function that takes in the number of dice, which is an int, and the n, which by default is 10,000, because now we want to sort of increase the accuracy a bit, and the y limit, which is by default set to 0 comma 1, right? Or uh, or y limit is none by default. How about 1? That's cool, right? So here we do the same thing for the roles. Where the roles? Yep, there we go. We do the pretty same thing for roles. So roles is that, only difference being uh, only difference being is we also take a sum of the roles, right, for the range n, and this is for the range of dice. So let me explain what's going on in this mess, right? First up, we are rolling a die for the range in dice. So if I put one die, this occurs once. You roll the dice once, and that gets iterated for a range of n, right? So let me actually have a sort of test cell here, where now if I say plot roles, and actually let's just print out the roles, and now if I say plot roles of 2, this is what I get for 10,000 times. And actually we want a really small n just for showcase, so we say n5. So there we go, we get in for 2 dice rolled 5 times. How simple and cool is that, right? So we are taking the sum of the rolled dice for a range n, which will give us the rolls, hopefully, right? Now let us programmatically define the range of our dice. If you look here, if you look right around, where did we go? Here, we arranged 1 to 7 because we knew beforehand that the one die will give us in a range of 1 to 7. What about 2 dice though? 2 dice would have been 2 to 13, and then 3 dice would have been 3 to 19. Noticing the pattern here, if this is x, we can call this x into 6 plus 1, can't we? This is x into 6 plus 1. You can try this, but you'll get the same formula basically. Now that's pretty cool. So what we can programmatically define here is the sum outcomes will be np.arrange dice and dice into 6 plus 1, and then our normal sum counts, which is like rolls dot count probability of occurring the sum value for some val in sum outcomes, right? So now we have defined our roles function. Now if I currently go print sum counts, right, and do this, there we go, we get a nice little probability, which actually makes more sense if I roll like 10 dice maybe. And see, there you go, that's our distribution. And since that is 10, we should get how much is that, 61, I guess, 61 attributes. Not, oh, sorry, no, not like that. Dot length, is that how you do it? No attribute n, does it? Okay, that's just printing it, right? You have to do like this, I guess. Am I wrong? No, that's not how you do it. I guess this is how you do it in Python. Yeah, there you go. Oh, why did I get 51? That's okay, so that goes from 10 to 61. So yeah, 51 is the right answer. And if I do 21, 21 should give it 106, which makes sense when I see 21 into 6 plus 1 minus 21 and little brackets, so I don't get confused with broad mass. 106, which is the right answer, so our function is working quite well. So there we go. Now that we have our sum counts, so our x will be the sum outcomes because we want to see for each outcome, and our y, which will correspond to p of x, will be the sum counts. Or better yet, let's actually calculate the probability of the sum counts like we did earlier, right? So now probabilities is np.array sum counts by n, right? So now probabilities, there we go. Now that we have that defined, actually it would really help if I also get the mean and standard deviation, so I can sort of predict where the peak comes, right? So how about I just go print mean and give a little space there, and actually I don't want the full mean. Let me do some like f string manipulation here, which will be np dot mean of the roles, and that is limited to 2 floats. I think that's how you do it. And I'm a bit flunky on Python. Oh, no. Yeah, I guess that's the right way to do it. I want the mean and standard deviation. No, that sounds weird. Let's just write standard deviation. STD, I guess. Am I right? Yeah, that's right. So there we go. Once that is done, we will now use a style called sns.setStyle of white grid. I hope that's right. I'm not really sure though. There's no this thing there, right? And we want the plot dot size to be quite huge, right? Or I guess that's called figure. Plot dot figure, and the fig size will be about 10 to 6. So it's nice and short. It basically fits. Now finally we say pyplot dot plot the sum of the outcomes and the probabilities. I always get the spelling wrong, so I just make sure to copy paste that. Yep, and the marker will be a nice little O, right? And the line style will be a dot, and the color will be red. And yeah, plot dot x label, if I'm spelling that right, will be the sum of dice rolls, right? And the y label will be probabilities. And finally the title, this is all just aesthetics, you can just end it with this line, but this is a YouTube video, we want to make it pretty, so let's do that. Probability distribution of rolling and dice, and then plot dot grid, let's also like give it a grid, right? So the axis will be y, the line style will be like dot dot, and the alpha will be 0.7, so I'm actually able to see stuff. And the plots x limit will be dice into 6, because that's all we'll be needing, right? And I didn't really specify the y limit, so let it just be none there. And yeah, if I do want to provide a y limit, when I do, please make sure the y limit is from 0 to y limit, so I can rest in peace. And finally plot dot show. Oh my god, that's a huge function, right? Not probably not that huge, but it at least felt huge on camera. So now if I plot the roll of one die, and we already have our first error, which I guess fixed size is not a function, right. That's why you need to do you need to use IntelliSense. It's y label, it's y label. There we go. So we have our funky little graph we got from earlier, and I guess 10 6 is a huge figure. How about 3? There we go, that's cute, I guess. And 4, yeah, we get our funky little graph we got from earlier. Mean is 3.5 and the standard deviation is 1.71. But now if I set the y limit to be 1, there we go, we get a nice little 1.66 graph we got from earlier. Perfect. Let's now plot the rolls of 2 die. How about that? There you go, we got our graph that I was explaining here earlier in this thing I made. See, there you go, same graph, the mean of 7 and a standard deviation of 2.42. so as you can see, this is not perfect, so if I run the reiteration again, we actually got a perfect 7. Hyped. So yeah, as you can see, the graph is slowly taking shape. It went from a funky little thing to, wow, that's way too funky, to something like this, which is a bit more royal. And now if I say plot rolls of 3, there you go, it started to take a curve, which is what we want. And no, I probably should have declared these as f strings. There you go, 1 die, 2 dice. Yeah, now it's showing up. Yeah, the probability of rolling 3 dice, which is slowly taking shape, and you can see the standard deviation to be 10.5 ish. So I can say quite confidently that if you are to choose a dice distribution from like, I don't know, 3 to 18, you would most likely choose 10.5. Do it for 4. Wow, taking shape. 5, taking shape. 6, really taking shape. But is there any way for us to know if, well, it's actually a normal distribution? Well, there is. You see, uh, we have a very handy little function from in SAPY, which hopefully I have installed. From SAPY import stats. Oh, there you go. That was quite simple. So there is a test which I am not really sure I know much about, but I do know that well, it gives you the distribution, I guess. So if I go probabilities right there, there's a stats value, and if I print out the test dot p value, or just p value, probabilities is not defined. Right. I need to do this in the function. Where's the function? Yeah, there we go. Mm, if I print that out there, and no, is it? Yeah, this is the value, and I guess so. This is not a normal distribution. This should be nearly 0.01 ish. I have to assume. So this is like less than or equal to 0.1 at least. Like let's set the bar really low, uh, like here, right there. Uh, Normal distribution is that. So oops, so yeah, this is not a normal distribution. uh, Neither is this a normal distribution, and 6 on the other hand might be looking to be a normal distribution, which is quite cool. And actually, let's start setting the bar higher up. So I heard that this is the ideal limit that most people use, and wow, that's actually giving us a normal distribution. Wasn't that a good this thing? Plot roles of, well, 13. Take some time to process, and there you go. It's starting to look more and more like a random distribution, right? How cool is that? 13 is right there. How about 21 or 31, which is said to be the limit from where the normal, the central limit theorem is usually valid for most data. And there you go. We have a perfectly normal curve. How cool is that? We have almost perfectly normal curve, and yeah, normal distribution is quite true. This is giving us a true statement, hence it is true. And although the test that we use to determine if it is normal distribution or not is not the most accurate in some scenarios, but it works for our case. I mean, it looks normal, it is normal. Ta-da. So yeah, we have a normal distribution, hence proved hence we proved this theory, right? How cool is that? So yeah, I hope you had fun watching this video. This was on my bucket list since a really long time to make, and yeah, hopefully you had as much fun as I did. Thanks for watching. See you later. Stay tuned for the tutorial series on my channel. I'll be releasing that one shortly. Thanks for watching. Goodbye.